All right, let's dive into this paper. The era of agentic organization. Learning to organize with language models, that's from Microsoft Research, and really shifts how we think about LLMs, right? Moving beyond just sequential thinking.
Definitely. It's about making them managers, not just workers.
Mm-hmm.
So the biggest thing here is this idea they call asynchronous thinking, or AsyncThink.
AsyncThink, okay.
Yeah, it's a new way for LLMs to tackle really complex problems. Instead of just, thinking step by step, it creates this collaborative setup, like a team of agents working together, but concurrently. They actually learn how to delegate tasks.
Okay, delegate. And how does that delegation actually happen? Is it like a built-in function?
It's based on what they call the organizer-worker protocol. And it's all text-based, which is kind of cool. The model itself generates special commands like fork to send the subproblem off to another agent, a worker.
Fork, like splitting off a process.
Exactly. And then there's join, which is the command to bring the result back from that worker and merge it into the main thought process. So you get this really dynamic, structured way of thinking unfolding.
And the payoff, is it faster, better?
Both, actually. That's what's so compelling. Their experiments showed AsyncThink cut down the critical path latency by 28% compared to just running things in parallel.
Yeah.
And it did this while matching or even boosting accuracy on tough math reasoning benchmarks like AM24 and AMC23.
Hold on, let's unpack critical path latency for a sec, because normally we just think about how long it takes, like wall clock time. This sounds different.
It is. It's more of a theoretical measure. Think of it as the absolute minimum number of sequential steps needed to solve the problem. If you have a task that could theoretically be done in 10 steps, but you can run, say, 8 of those steps at the same time.
Then your critical path is just those remaining 2 sequential steps.
Precisely. AsyncThink is specifically designed and learned to minimize those points where everything has to wait for something else. It maximizes the concurrent parts.
Got it. Okay. And the last key bit you mentioned, generalization.
Yeah, this was pretty striking. They trained the model only on these multi-solution countdown number tasks, but then they tested it 0 shot, no extra training on something totally different, like solving Sudoku puzzles.
And it worked.
It worked surprisingly well. It successfully applied this whole complex fork-join organization structure. It showed the model didn't just memorize how to do countdown problems, it learned the skill of organizing thinking asynchronously.
Wow. Okay, so that really sets the stage for this whole vision, the era of agentic organization.
Exactly. We're not just looking at LLMs as individual thinkers anymore. We're thinking about building, organizations out of them. Teams that can do more than any single model could alone, or faster.
Right, and this is different from what we've been doing, because multi-agent systems aren't totally new.
True, but previous approaches mostly fell into 2 buckets. You had purely sequential thinking, like your basic chain of thought, one step after another. Simple, but slow for complex stuff.
Okay, CO key. And the other?
Parallel thinking. This is where you might kick off, say, 4 different chain of thought processes independently on the same problem. Then maybe you take a majority vote on the final answers.
Right, like running multiple simulations and seeing what most agree on. That sounds like it should improve things.
It can improve robustness, yeah. Get better answers sometimes. But it has some major drawbacks, which AsyncThink tries to solve. The big ones are latency and rigidity.
The latency again. Let me guess. If you start 4 independent thought processes.
You have to wait for the slowest one to finish. Even if 3 are done super quickly, if that 4th one takes ages, your total time is dictated by that straggler. Plus the time for the final aggregation step. It's just not efficient in terms of speed.
Yeah, that makes sense. And rigidity.
Well, those parallel methods are usually quite fixed.
Yeah.
To decide up front, okay, we'll run 4 chains and vote. That's the plan. It doesn't adapt. It can't get an early result from one chain and use that information to maybe change what another chain is doing or launch a new, more specific task.
I see. It's a predetermined structure, not a dynamic one that responds to the problem as it unfolds.
Exactly. It relies on us humans designing the workflow beforehand.
The paper uses a neat computer systems analogy here, which I think helps clarify this. They say, think of one LLM agent like a single CPU core.
Right. And the agent pool, the total number of agents you have available, that's like your multi-core CPU. It sets your maximum parallel processing power.
And the key difference with AsyncThink is this learned organization policy. That's like the multi-process program itself, the smart software that knows how to schedule tasks efficiently across all those cores.
Spot on. AsyncThink is about teaching the LLM to basically write its own efficient multi-process program for whatever problem you throw at it, dynamically.
Okay, so if the goal is this adaptive policy, How does the organizer-worker thing actually work under the hood? You said they share the same LLM.
Yeah, same base model, same weights. The difference isn't in the model itself, but in the role they play and the actions they're allowed to take during generation. You have a total agent pool capacity, let's call it CN. One agent is designated the organizer.
The manager.
The manager, exactly. It handles the overall coordination. The other CDAO agents are the workers ready to take on tasks.
And the communication is all through those text commands. You mentioned 4.
4 core actions the organizer can generate. The simplest is think. That just means the organizer keeps generating text sequentially in its own thread, doing its own reasoning.
Standard procedure.
Right. Then comes fork. This is the delegation. If the organizer decides part of the problem can be solved independently, it generates a special tag in its output, like FORKI. Here's the subproblem, FORKI. It's just an ID to keep track.
And the system sees that tag and sends the here's the subproblem part to a free worker.
Precisely. It extracts the query, assigns it to an available worker, and tags it with I. But there are constraints.
Like what?
Well, it can't fork if the ID is already being used by another active fork. And it can't fork if all C1 worker slots are already busy. That prevents chaos, basically. Keeps the system manageable.
Resource management built in. Okay, so fork sends work out. How does it come back? That's join.
That's join. When the organizer needs the result from worker I, it generates JOINI. Now, here's the asynchronous part. If worker I hasn't finished yet, the organizer's own thinking process just pauses. It waits.
It waits right there, mid-generation.
Mid-generation. It doesn't waste time doing other things. It waits specifically for that piece of information. Once worker I finishes, its entire generated text output gets inserted right back into the organizer's context.
How does that look? Does it just appear?
It gets wrapped in tags like JOINI. Here's the result from the worker JOINI. And as soon as that's inserted, the organizer resumes generating, now with that worker's result available in its history to inform the next token it predicts.
Okay, that's clever. So the knowledge from the parallel tasks gets seamlessly integrated back into the main flow. It feels very dynamic.
It is. And it all happens just by manipulating the input and output text of the LLM. No changes needed to the underlying model architecture. The fourth action is simple. Answer. That just tells the system the final result is ready and terminates everything.
And you can see how standard sequential thinking is just using the think action repeatedly. And basic parallel thinking is like doing a bunch of forks right at the start, then a bunch of joins at the end.
Exactly. Those become just specific, rather rigid patterns within this much more flexible framework. AsyncThink learns to use the full range of possibilities.
But how? How do you teach a model, which is fundamentally just predicting the next word, to become this smart scheduler, optimizing for speed and accuracy? The training must be key. They use 2 stages, right?
Absolutely critical. You're not just teaching it what to think, but how to organize the thinking. Stage 1 is what they call cold start format fine-tuning, or SFT.
Cold start SFT. Why cold start?
Because this kind of tagged asynchronous thinking data just doesn't exist naturally in web text or books. They had to create it. They actually used GPT-4o to analyze problems, figure out which parts could be done independently, and then generate example traces using the fork-join syntax.
Bootstrapping the training data with another powerful model. Okay, but why is this SFT step necessary? Couldn't they just jump to optimizing the policy?
They found that if you skip SFT, the model often gets stuck in bad habits. It might learn to just always fork, then immediately join, which is basically just slow sequential thinking. Or it might do a simple parallel, fork everything, then join everything. The SFT stage teaches the model the grammar of fork and join, makes it comfortable using them, and gives it enough flexibility or plasticity so it doesn't just collapse to the simplest strategies later on.
Okay, so SFT lays the foundation, teaches the rules, then stage 2 is where it learns to play the game well.
That's the reinforcement learning RL stage. SFT teaches syntax. RL teaches strategy. They used an RL technique based on GRPO group relative policy optimization, which is suited for optimizing policies across multiple possible execution traces.
And the reward signal, what tells it good job or bad job, that must be complex too.
It had to balance 3 things. First, obviously, accuracy reward, $3. Did it get the right answer? That's table stakes. Second, a format reward. This penalizes the model if it messes up the protocol, like trying to fork with an ID that's already in use, or trying to join a result that was never forked, or using more workers than available. Basic rule following.
Okay, correctness and playing by the rules. What's the third one? This must be the efficiency part.
Exactly. This is the secret sauce for speed, the thinking concurrency reward. This reward explicitly encourages the model to keep its workers busy. It measures the ratio of how many workers are active compared to the total time.
The concurrency ratio.
Right. And it rewards policies that achieve a higher concurrency ratio. It directly pushes the model to fork tasks out whenever possible, rather than doing them sequentially itself.
So ROD is basically teaching the model impatience in a good way. Maximize parallelism to minimize that critical path time.
That's a great way to put it. It's the incentive that shapes the LLM's behavior from just a thinker into an efficient organizer, driving down that latency figure we talked about earlier.
Okay, let's look at the results then, because usually you trade accuracy for speed or vice versa. Did AsyncThink manage to beat that trade-off? You mentioned the math benchmarks AM and AMC.
They really did. On AMC 23, for example, AsyncThink hit 73.3% accuracy, which was right up there with or better than the parallel baselines. But the critical path latency dropped significantly from over 2,000 tokens for a strong parallel baseline down to about 1,460 tokens for AsyncThink.
That's a big drop. And remember, they limited the workers, right? The workers couldn't generate super long responses.
Yeah, workers were capped at 512 tokens. This wasn't about letting parallel processes run massive computations. It showed that breaking the problem to smaller, quickly resolved chunks, coordinated by the organizer, is more efficient than just running long, independent parallel thoughts.
That efficiency came through even more strongly on the multi-solution countdown task, didn't it?
Oh, absolutely. That task requires finding all possible solutions. AsyncThink got 89% all correct, which crushed both parallel thinking, around 69%, and standard sequential thinking, around 70%. The learned organization policy was just much better at exploring the solution space effectively.
And the ablation studies really underscore the training method, taking out the SFT stage.
Accuracy tanked.
Yeah.
It showed you really need that initial stage to teach the model the structure and possibilities of fork join before you can optimize it.
And taking out the concurrency reward.
The system basically reverted to being slow. The concurrency ratio plummeted on the math tasks. It went from almost 45% down to about 26%. Latency went right back up. It proves that RIDE is absolutely essential for teaching the model to prioritize speed and parallel execution.
But for me, the most impressive part is the Sudoku result. Training only on number games, arithmetic. And then it successfully organizes itself to solve Sudoku grids.
Right, a 4x4 Sudoku, which is all about spatial constraints. The model hadn't been trained on that type of problem at all, but it transferred the skill of organization.
It learned how to manage complexity, how to decompose and delegate.
Exactly. It figured out when to fork out parts of the Sudoku problem, probably assigning different sections or hypotheses to workers, and then when to join the results back to check for consistency. And it didn't just work. It got 89.4% accuracy, again, beating the parallel baseline, and it did it faster.
You can really picture it with the math case study they included, a tricky geometry problem.
Yeah, where the best way to set it up wasn't obvious, instead of the organizer just guessing one method.
It forks it out. It sends the same problem to 3 different workers, but tells each one. You use the coordinate method. You assume a unit edge length. You try this other geometric approach.
And because they run concurrently, the organizer quickly gets back multiple perspectives. It can check if they agree, find errors faster, or build confidence in the answer. It's like a really smart project manager using parallel tracks for verification and exploration.
So stepping back, what's the big picture takeaway here? AsyncThink seems to crack that fundamental trade-off.
It really does. You get the accuracy benefits that often come from exploring multiple lines of reasoning, like in parallel methods, but you avoid the huge latency penalty because the system learns to coordinate dynamically and asynchronously.
The LLM isn't just generating text, it's learning to generate the optimal schedule for its own thinking process, predicting the next best action fork, join, or think to maximize both speed and correctness.
It's a profound shift in perspective. The model becomes a self-organizing entity.
And the future directions they sketch out are pretty mind-bending, scaling this up.
Yeah, scaling agentic organization. Not just more agents, but different kinds of agents. Imagine an organization with specialized math agents, coding agents, agents equipped with web search tools or code interpreters, all coordinated by an organizer.
A heterogeneous team of experts.
And then there's recursive agentic organization. The idea that a worker, if given a really hard sub-problem, could temporarily become a sub-organizer itself.
And fork out tasks to its own team of sub-workers. Wow, that's like hierarchical management structures emerging naturally.
Exactly. You could tackle incredibly complex, deeply nested problems that way.
And finally, they touch on bringing humans into the loop. Human AI agentic organization.
The framework already supports it, conceptually. An AI organizer could literally generate F4K human. Please verify this step. F4K human, routing a task that needs human judgment. Or a human could act as the top-level organizer, directing teams of AI workers.
It turns that multi-process program analogy into potentially a real collaborative structure between humans and AI, which leaves us with a really interesting thought to ponder. If this framework allows the LLM to learn an organization policy that optimizes for speed and accuracy based on the reward signals, could we change those rewards? Could we train it to optimize for, say, minimizing the cost of computation? Or perhaps maximizing the explainability of the final answer, maybe by rewarding policies that join frequently with intermediate reasoning?
That's a fascinating question. The organizational policy framework seems general. The rewards define the objective. So, yes, perhaps we could shape these agentic organizations to pursue entirely different goals beyond just speed and accuracy. Something for you to think about.